Imagine a world where your phone never heats up while charging, or power lines transmit electricity across continents with absolutely no loss. Picture magnetic levitation trains gliding effortlessly without expending vast amounts of energy to maintain their lift. That ideal scenario is the promise of room-temperature superconductors, materials that conduct electricity with zero resistance at everyday temperatures. Currently, achieving true resistanceless conduction at room temperature remains one of the grand challenges in physics and has not yet been definitively proven or replicated. The reason zero resistance is so difficult to achieve boils down to how electrons move through a material. In normal conductors, electrons constantly bump into atoms and imperfections within the material, causing them to lose energy as heat. This friction is what we call electrical resistance. For a material to be resistanceless, these electrons need to flow freely without any scattering. Superconductors achieve this by forming special partnerships called Cooper pairs. These pairs, instead of scattering, are able to glide through the material as a single entity, bypassing obstacles without losing energy. However, these delicate Cooper pairs are easily disrupted by thermal energy. At higher temperatures, the atoms in the material vibrate more violently, shaking apart these electron partnerships and destroying the superconductivity. This is why most known superconductors requiring extreme cooling, often down to hundreds of degrees below 0 Celsius, to exhibit their remarkable properties. Scientists are actively searching for new materials and conditions where these Cooper pairs can remain as stable and resist the disruptive effects of thermal vibrations at much higher, even room, temperatures. This involves exploring exotic compounds and subjecting materials to extreme pressures, which can alter their atomic structure and electronic properties in ways that might favor superconductivity. The quest often involves intricate quantum mechanical calculations and precise material synthesis to engineer the perfect atomic lattice. Researchers are essentially playing a high-stakes game of molecular Lego, trying to build a structure where electrons can dance unimpeded. The holy grail in this field is to find a material that is a room-temperature superconductor at ambient pressure. While conventional superconductors operate near absolute zero, the discovery of what are called high-temperature superconductors in the 1980s, which work at liquid nitrogen temperatures, showed that the temperature barrier could be pushed significantly higher. More recently, there have been fascinating claims, such as the one surrounding LK99, about materials showing signs of superconductivity at room temperature and pressure. These claims, while incredibly exciting, undergo rigorous scrutiny and requiring independent verification, which is a fundamental part of the scientific process. These scientific investigations are crucial because reproducibility ensures that a discovery is real and not just an anomaly or experimental error. Ultimately, cracking the code of room temperature superconductivity would revolutionize our world, leading to ultra-efficient power grids, incredibly fast and energy-saving computers, advanced medical imaging technologies like MRI machines that are cheaper and more accessible, and even powerful, compact fusion reactors. It is a quest that continues to inspire physicists, pushing the boundaries of what we understand about matter and energy, and promising a future where energy efficiency is no longer a dream but a fundamental reality.